Hello and welcome to video 6 in 3D on the Nintendo 64. So in this video I will show you how to make a scroller in 3D from a 2D level, and I'll go over how I did it and how you can do it also. So let's jump into this. So the topics I will cover is third person camera, how I go about setting that up, things you should know when scrolling large levels. I'll go into how I am handling it in this program. I'll then go into how I am handling some of the platform collisions with the actors. I'll then go into how I created the 3D levels from 2D levels. Then I'll quickly go over the actor jumping and falling code and try and explain that as best as I can. Then I'll go over the simple enemy movement, how that works, and then I'll talk about some issues I had when I added lighting to the game. So first off, I will show you the actors in Blender. So we from the last video on animation, we have our Mario player here, and then there is also a Luigi character now, which I created using the same assets of Mario and then just tweaked the sizes for Luigi. You play as him on level 2. And then we also have our updated Goomba here. Which now has the original NES style. However, if you wanted to switch out for the Super Nintendo style, the head is here, and you could always use the texture from the previous tutorial. So those are the actors, and then we have some parts for our level here. So it will probably help if I bring in a 2D level here so you can see what we're working with. So our floor tiles here are represented by our floor blocks. If I hide that one. So here's our floor block. So you'll notice that the cube has the texture scaled a number of times here, and the reason for this is, as the game is going to be converted to 3D, the x-axis which we would scroll over is actually going to be the z-axis in 3D. The y-axis stays the same. So the x-axis is how wide the platforms are, and I found that by having it like 3 wide works fine. Of course, in your own sort of games, it'll be up to you to decide the sizes of in-game objects. So in the case of the cube here, it would actually be 3 wide like this, so you can see that it'll be 2 blocks high by 3 wide there. So that's a floor block there, and then I decided to create coins to put in the game rather than, if you look at the original sort of NES Mario game here, everything revolves around jumping up into blocks. But obviously, because we're going to be in 3D and viewing it from a third-person camera, you would be under this here, and then once you sort of jump up, you wouldn't actually see anything happen. So it kind of removed this whole jumping up into things business from the original NES game, and instead replaced collecting coins instead, which is obviously fitting with the more modern sort of Mario games. So here's our collectible object here. We have our coin. And then we have our normal bricks here. And then we have a block. So you encounter these later on in these levels here. Just scroll through here. Here you go, that's where these appear. And again, these are 3 tiles wide to cover the whole width of the level segment there. So hide those, and then obviously once you've completed the level, you've got to the end here. There you go, here's our flag. So in the case of this one here, here's our flag, and then we have the flag base and the flag pole. Obviously these are all scaled for export here. Obviously in the game itself they'll all be scaled to their correct sizes. And then we also have the pipes as well. So the reason why there's 2 of these pipes is they obviously need to expand across the whole width of the level. This will make sense when I run the demo in a moment and show you. And then we have the tops of the pipes here. Again, these will all be sort of scaled to fit the world. So one thing to note, so if I'm looking at these objects front on, I'll select it. Most of these objects, their origin is at the bottom left when they're exported. So the bottom left is normally at 000 for all of the background objects. This is just so that they align nicely with the actual world for easy positioning. However, when it comes to the pipes, I had to change this. So you see their alignment, their origin is actually at the top. So you'll see here, obviously that's one sort of a tile high, although it's kind of 2. But then later on, the pipes themselves vary in size. So here we have one which is kind of like 4 high, then 3 high, and then 2 high again. Initially I had designed things so that they would just be like one segment here, so the pipe would be split into like tiles like it is here. But when I added lighting, that sort of broke everything, which I'll talk about a bit later. So this is why the pipe parts, or rather the pipe bottom, has its alignment there. Same with the pipe top as well. Although this is just now, this just covers the bottom pipe parts slightly. So those are the models used. So I will now open up the demo and show you. So another thing to note as well is there's like a few versions of this while I was tweaking around with things. This is the final version here. So this is the original title screen, just tweaked slightly. The colours are changed, and I've added Luigi in there as well on the title screen here. So if we press start to play, so this is obviously running a bit slower because I have a load of other things running on the desktop here. So as you can see here, the Goombas get crushed, and then there's another sort of model for them being splattered there. So as I said, if you look here, you'll see the world is 3 tiles wide. And here's our first set of pipes. I won't do the full level. So one thing to note as well is there's variable height. So if you just quickly press it, you'll jump that high. If you hold it down, you obviously jump a lot higher. The Goombas do actually track you as well. So I won't do any more of the game. I'll allow you to download the demo and have a look for yourself. So there's 2 levels. There's there is the first level here, which is built from this level map of the first level, and then there is also the underworld level as well, although this one's been tweaked a bit more as I removed the ceilings here, as they could interfere with the third-person camera in 3D. Not all of these objects are obviously in the game here. I didn't add in the Koopa Troopers here, or the plants, or the platforms. So there are some differences. So I'll now go over the key parts which I think you should know to enable you to get up to speed with creating your own 3D levels. So the third person camera, how's that actually working? So there are a number of things we need to know when we work with the third person camera code. I find a decent way to sort of do this is we position the camera behind the target we wish it to follow, and then beforehand we set 3 key variables. We have an above value, a behind value, and an in front value. The reason why we have an in front value is if we only targeted the actor we wish to follow, then we wouldn't actually see in front of them most of the time. So to enable us to actually see what they are seeing as well as them, we kind of have to put in a distance in front of them to point the camera at. So if I jump into the camera code here, This structure here is what we use for this here. We have free floats here, and above, behind and in front value. And then I'll set these somewhere. Let's have a look. Where did I put them? Is it in here? No. I might have put it in the LevelManager actually. Okay, so there's the camera distance behind. Could be in the game itself actually. Let's see where he's setting these. Let's check where it's actually being set up a moment. So there is a camera initialized bit a moment. Must have gone past it. Oh, here we go. There are some fixed values here. I know I put them somewhere. Normally I put them in the header file. Anyway, so these are the values I've sort of played around with and found work fine. So have a play around with those. So you could obviously zoom out from the player by changing the behind and the above values. So if I jump into the actual camera thing itself here, so the initialize function, all it does is the key parts we're interested in are these here. So we plug in the above, behind and in front values into the follow structure here, and then we use the yaw of the actor and its position, and then we basically calculate the X and the Z position behind the player, and then put those into here, and then use the in front value using the yaw of the player to calculate the look value of the camera being in front of them. And then we subtract 1 from the target Y value, just so that the look and position Y's are not the same. So that's how that is done, which basically gives you this here. If you can visualize what you're doing as this, then it will kind of make sense. So you can kind of play around with these numbers here. So now let's get into the most complicated part, the actual scrolling itself. So as I was showing before, the levels themselves, you can find online whole images like this where people have painstakingly exported, I guess, screen prints and then stitched them all together to highlight the whole level. That was in the NES itself, and they've also highlighted hidden objects as well. And then using the show grid here, I'm able to show you how big each tile potentially was in the levels. So on the NES itself, this kind of highlights the actual view of one screen here, what could actually be seen. So you'll see here there was actually 16 of these game tiles across by 15 down. So I decided to kind of almost match that to some degree. So the easiest way to kind of convert this into a level map for ourselves, you could simply, once you've changed the show to grid like this, and then you've put in a size. So if we go to grid settings here, you'll see 16 by 16 pixels. And then if you look at these numbers here, the last two numbers, so you'll see that shows you what tile on this image the cursor is actually in. So if you scroll right to the end of the level here, you see that size there is 223, so that's actually 224 by 15 tiles. So you could then create an image which is that size in pixels. So if I side by side these a moment, so down there we have the actual NES level here. And then up here we have our tile map representation of these levels here. So you'll see here this is this here split into segments. So you'll see that there are some changes here. So these pixel colors, this top line here is basically like a key to this level. Each of these pixels represents one tile type in game. This magenta color here represents a floor tile. And then these grey colours here represent the bricks themselves. So as this is in 3D, to give like some width to these tiles, you can literally just change the add another colour, and then one tile can be like one width, and then another colour can represent a tile of a different width in the 3D level itself. And then the yellow pixels here represent the coins on the level. The red pixels represent the Goombas here. So obviously there was one to start with here, decided to add another one in there just for a good measure. And then another thing to note here is these green pixels represent the pipes. More importantly, they represent a height that those pipes should be. So the only one we record here is actually the height of the pipe. This dark purple here is just like a spacer to indicate to myself the size that these tiles will actually fill in the world. So this pipe here will actually extend 2 tiles in depth and 2 tiles in height. And then here, this lighter green represents a taller pipe which takes up 3, and then obviously this other one takes up 4 there. And then you can see here going across that it kind of, some parts match the NES level where it kind of makes sense. Obviously some of the actions kind of lacking in the NES version. Some of it actually makes sense for 2D, whereas in 3D, and in this case I decided to add more to give some more action. So this bit here is the start of one of these, and what you'll notice is that there's an empty space in here. And the reason for that is there's no point putting in these other tiles, because obviously in 2D you can see them because we're viewing them from the side. But in 3D we'll be viewing them from outside of this via the player, so you'll never actually see the sides of any of these. You'll only see them front on or from above, so we can get away with not drawing certain parts here, which you can also see here as well. And then the final bit here, obviously again there's no point drawing all of these hidden ones in here. And then the blue colour here, that represents the flag, and obviously there's no real reason to draw the castle here. That would just be extra work for the sake of it, which is outside of the scope of this video here. So these tiles here represent a block of 16 pixels on the level here. So that kind of shows, or that should hopefully show to you how I've converted the level maps themselves into tile maps here. So another thing to note as well is I exported these with my DS to tile graphics converter as a 256-bit image. But when I exported these, you want to export these in columns. So it will then look like this. And the reason for this is when we read this back, we are just reading a strip at a time. As the level scrolls, we are literally just going to read one strip at a time from the 2D level and then convert what we find into 3D blocks. So you can think of this here as the scroll window, if you like. So what this is actually doing, this will be following the player, and the origin of this will be at the top left here. And then what happens is, as this moves, whatever is actually inside here will be given physical properties and in a sense will become alive. And only the things inside of this scrolling viewport will be able to be collided with as soon as this scrolls here. So once it scrolls past this Goomba here, he'll then be removed from the game world, if you like, or the level world, as there is no point keeping track of anything outside of the viewport here. We literally limit what we give physical properties to. This is handled in the LevelManager code, which I'll jump into in a moment to go through this here. So what we do is we kind of create like a container, or like a pool, if you like, of objects in the LevelManager. And then when we read back the level tiles from the level data, so like I said, we take one column of these, we then add them to the entity container in the LevelManager. This ends up with like a fixed amount of entities that can be alive at any one time, and it's only those entities that we check for collisions with against our player. The enemies themselves, they get spawned from the viewport once it sort of crosses the level data where their tile is. So another thing that I don't do on this level as well is I do not allow you to scroll backwards. So the window will follow the player when he moves forward. So you can move forward. So say our player was, if I just grab this one here a moment to illustrate this. So our player, whenever he moves past a certain point, the scroll window will follow him. However, he can only go this far back. The scroll window will not move back. The reason for that is if we start going backwards, then everything will start spawning again that we've collected. You would kind of have to create like a separate list of entities for the like duration of the level if you wanted to give them semi permanence, if you like. So to get around that, the player can obviously move back. They can even move outside of this. But obviously the window itself will not follow them, and everything past the end here will not be there. So you kind of have like a void forming behind you. So as you move forward, this moves forward, and everything outside of it behind is removed and ceases to exist. At the start of the level, we read all of these columns here for the full width of the viewport. So we have like an area we can actually see at the start, and only then after that do we just constantly add and remove new objects as and when they come into the viewport. That's kind of, I'm sure that's how it is handled on all of the Ode 2D games as well, as we obviously only have limited processing power to work with. So you only give it to things that make sense. So things that are nearby are the only things which the player can actually interact with, and the enemies themselves as well. They are only able to interact with other sort of background entities in the viewport. So as soon as if this was an enemy here, as soon as it goes out here, it then ceases to exist. So you kind of have like a limited pool for entities, and one for enemies as well. This text basically just says the same thing here. So I'll jump into some of the LevelManager stuff here. So if I come up here, where we have a list of, here we go. So the maximum objects we can have is 250. And so these are some constants for tile sizes here. This is a level strip width, how wide they are. And then, as I said here, from that other sort of picture here of being 224 pixels wide. So the next level, the underground one, is not as wide as this one. So these are some fixed constants here for our levels. So the window size in tiles is 16 by 15. So that's basically the viewport there. And then if I bring this one up here. So this array here handles the level objects. And then we have some functions which handles culling them. So the scroll window rectangle, where is it? Here we go. This one here is basically our viewport, this rectangle here. So when a level is started, I'll scroll down to the level initialize code moment. You'll see the window is set up to the level map width and pixels and heights, which is basically these two variables times the tile depth and the tile height. And like I said here, this level is the x-axis here is actually the z-axis in our 3D game. The y-axis maintains, it's the same thing. The only thing we need to take into account is that in 3D, the y value of 0 is at the bottom, whereas in 2D, it is normally starts at the top left of the screen. So we have another thing here which handles that for us. This define here, the map ceiling. So we have the level map height -1, which is here, times the height in tiles. So a tile height for our game is 5 here. I found this this works fine. And then we have like an old scroll X position here. And then there's only two levels which I put in here. We have the this one here. So this is the first NES level, and then there is the underground level here. I'll obviously include these images for you so you can have a play around and have your own levels here. I only include two. And then to create our objects, so let's first discuss what properties they have. So this is our structure that handles level objects. So one thing to note is what happens when an enemy is found. So when an enemy is encountered, we tell the baddie manager to actually add them. So it has its own sort of container where it holds on to active baddies, and it will check against the level scroll window here. Where are we here? What was I called? There we go. The scroll window here. It will check against that to see whether to keep that enemy alive or whether to get rid of them. So you kind of hand up like a cache or a pool of entities, if you like. This also adds a little bit more complexity to spawning and removing them, as the amount of them is obviously dynamic and will rise and fall. So I think that kind of covers most of this here, what I was saying here. Yeah, this is kind of the same how it works for 2D as well. There's only like a limited amount of sprites that the NES could obviously have and kind of draw at any one time. And the same kind of applies with the other like old consoles as well. Anything that kind of had like 2D with tile maps. Again, there's only so much you can kind of check for collisions with at any one time. I'll obviously jump back into some more detail in a moment with the LevelManager. So one thing I will sort of quickly go over is I'll show you the sort of spawning process, if you like. So when we start a new level via LevelManager init, obviously enters here, and then we have like a pointer which points to the level data, which, like I said, is exported in columns, which is why it's all one long line like this. So we kind of have to go over the level in columns. Usually I do the Y first by the X, but obviously because we're now working with columns, we need to do a whole viewport full, which is why we have the level view width in tiles here, and then the level view size in pixels here. this one here is actually the full level width in tiles. I think this is I think I use this later on to stop the actual scrolling viewport going outside of the level map. You obviously need to make sure that this window here can't go past here, so it needs to stop there, and obviously it can't go past the end of the level here, so you need to record the full width of the actual level, and obviously the width of the viewport itself, to prevent that from occurring in the LevelManager code as you scroll along. So in the initialize bit here, we obviously take a tile from the level data here, and then using the switch block we then try and figure out what tile it is, and then we either call the LevelManager add object if it is a background object, or in the case of a player here, we literally just initialize a vector 3 with the position of it actually in the world. So as I was saying here, this value here, so this ceiling value actually represents this sort of pixel here in the world, if you like. But as we are converting this to 3D, this is obviously up in the air, so we need to subtract whatever Y position from this to get the correct value to position our tiles in the world, which is what this does. This basically the Y position of our sort of actors will be at the very bottom here. So here's our actor. The origin for the tile would be the bottom left here. And then when we add the X and the Y position here from this loop, the baddie manager obviously carries out these same actions for the Goombas position as well. So I'll go over the add object in a moment here. So first off, I'll talk about what these things actually represent here. So we obviously have an object type ID, which is these, and then there is an object ID which represents its number inside the objects array here, and then we have a cube object, which is what we use for collisions throughout the game. So this cube object here, we have a vector 3 which represents its actual position, and then we have another vector 3 which represents its volume. And then there are some different functions for that here. So the key one for everything is the cube collides function. And then there's another useful one here, which is a center vector 3 on the cube itself. So this is useful for positioning a collision cube on an actor. And then depending on the origin of the actor, depends whether you wish to center the height of the cube with the position of the actor. Most of the time, I think all of the time actually, this is not actually done in this game here. As the origin of everything is usually at the bottom of the model itself. So for example, the block here, if I click on this, you'll see its origin is at the bottom here. Same with Mario here. The origin for this actor here will always be in between, center in between there. So this is how we sort of handle the collisions in here. So going back to the initialize function here, where is it? So we have like a generic function here for adding like a game object. The add object function here, what this takes in is the X and the Y tile position and the tile ID. So these are all the tile IDs here. These should match these here. So you'll see here the floor, which is tile 1, is the magenta here. And then there's two different brick types. As I said here, there's like a narrow one and a wide one. Which are these? And then this is where the magic comes in for creating them. So the defines for all of these, you'll probably have to go backwards and forwards to try between the header file here, these various sizes, with these here to get an idea of how these are actually sort of scaled and created. So this scale thing here is basically the size we plug into the collision cube of the background object itself, and sometimes it's also the same as the size the actual model, or sorry, mesh will be when we draw it. And then we add a collision object type as well, which will be useful for determining what the thing actually is that we've hit. So one thing to note here is, as this function is used over and over again, the ID for the object, we have to ask the level manager to get us a free object ID. So all that does is, so you'll see here there is a boolean to say, is this object alive? Basically we need to know which object is free from our bucket of objects, which we will reuse over and over again. So if we find, we start at the beginning first obviously and iterate over the whole array. If we find one that isn't alive, then we return its ID. I'm not actually sure whether I could have reduced this number or not. I think it was a number I sort of started out with as a good number to work with. Some of this will be trial and error, depending on the amount of blocks you have in view in one area of your level. if it returns -1, then obviously that will be a very bad thing, because that will signify we've run out of objects which we can actually use. So this is something you would kind of have to play around with when you sort of design your game first off, is to try and figure out, if I come back to here, try and figure out how many tiles will ever actually be active at any one time for the backdrop objects. This will obviously depend how wide or tall you have your viewport. So hopefully we will always find one which is alive, and then we can return its ID for reuse. And then we set a pointer to that object. We then work out, based on the tile position, where it should be in the world, which is what we do here. So one thing to note as well is, as this is obviously a 2D game, we have no sort of concept of depth, as in how wide it actually is. So one thing I sort of decided in this is, at the start, the X position will be equal to the depth of one tile, which in this case is 8. That's the starting X position. So the reason for that is, as the levels are actually 3 tiles wide, so the depth is 3 blocks across, I decided that 0 would be the sort of starting point, and then you would go to the maximum of 3 tiles wide. So the center point is this here. As if we have just something that's only 1 tile deep, then we want it to be centered on the x-axis. And then, as I said, the tile X here is actually the world Z here. Hopefully you won't find this too confusing. If not, then you'll just have to play around with things more until it kind of makes sense. So as the floor object is 3 tiles wide or 3 tiles deep, we set the X to 0, as it will be 3 tiles wide here. We then set the object to alive, and then we plug in what mesh we're going to use and what texture we're going to use. So we set the collision box, or cube rather, and then the actual model's size and position in the world. And then we always have to increment the object count once we've done that. So you'll see for a brick which is 1 tile wide here, that things are set up slightly different, so it doesn't change the px at all, and its width is only 1 tile wide. And then we come to a wide brick, and this is the size is obviously pretty much the same as the floor here. So these other blocks are kind of the same pretty much. So where it gets different is with the pipe. So here we only actually record one object for the pipe. And then if I come down here, you'll see that there's 3 different pipes here. As I said, from here we have 3 different colors for the pipes, and we only record the top position. So for this here, this is a height 2 pipe, which is this type here. So you'll see the X position is set to 0 as it needs to block the player. So its width needs to be the tile strip in width. So this is where the collision cube and the mesh or models scale differ from one another, as the scale here obviously refers to its actual mesh to match that of the world. So like I said, there's this here needs to be scaled to match the width of the floor, and we need to scale this down to match the height and tiles here. But because of the issues that happened with lighting, we add on more height. So what actually happens is this ends up being dug into the floor once it's actually created. So you'll see that the positions and the collision sizes don't match, whereas once you view them in the actual game world or level, they do align, as the cube obviously does actually overlap totally. Talking of which, there is, I'll just go to the game a minute here. Yeah, this will I'll run this again a moment. So if you press the left shoulder here, then what we actually do is we draw the collision boxes. This was handy for debugging, so you can see exactly where the collision boxes for things are. So that's useful for debugging, to make sure that the collision cubes actually are being aligned with the actual visual representations, the models themselves. So this obviously just changes the heights of them. And then the coin is slightly different again. So its collision object is slightly different to its visual object. And then you'll see here there's only one flagpole object. So when we come to draw in the flagpole and the pipe, just come to the render functions here. So there's another thing to note here as well, the collision type coin. It adds like a rotation to the model when it draws it. So if the model being drawn is a pipe, then we also draw the mesh for the pipe top on it, and we change its scale on the y-axis to only a tile half height, which is basically 2.5 in this instance here. That's how we're kind of handling that, because the position of the pipe is obviously at the top left, so we can literally just draw the cap of the pipe top on at the same location. And then this bit here is for if we go in to draw the collision box objects only. So I think that's most of the LevelManager stuff done there. So let's go into how I did collisions with platforms. So to give the impression that our actors are on the platforms, we obviously need to constantly check, as they could have moved off. So one of the things I did was I give them some properties which correspond to what they are doing, what's happening to them. So in the case of our player here, we have a player states flags, and then in the utilities header here I have all of the various entity states that our entities could be having done to them or doing. So as they are organized as bit flags here, they could be having multiple of these things happening to them at the same time. So it's important to get a feel what they're doing. Are they jumping? Are they walking around? Are they idle? Regardless of what they're doing, we still need to know whether they are actually on a platform or not. So you see here I have, for the player, I have two collision cubes. We have one for if they are hitting the background object, and another for if they are hitting like a Goomba or a coin. So if I open up the player code here, so there's a number of times here that we are checking to see whether they're on a platform or not. So this is the fall function here. So before we do anything, we align the background collision cube to the player. So you'll see here we have a vector 3 for the player's position. This point here is always under the, or between the player's feet. So the first thing we do is we center a collision cube on the player. So what this will do is it will align it to the player, if you like. So if I bring up here, so first off the cube would be aligned to the player here. So you see here the this rectangle here is aligned to the feet of the Goomba here. And then we have a couple of different collision functions in the LevelManager code here. So there is one specific for have we hit a platform. All we want to know is yes or no. So how that works is we take in the collision cube, then we create a temporary pointer to the LevelManager objects container, which, as you'll remember, holds only the objects which are nearby and inside the viewport. Then what we do is we take the collision cube and then we subtract a Y adjust value to it. So what that does is it moves the collision cube down slightly to make sure we get a good collision with anything that's underneath the actor. And then once we've done that, we then check to see whether that cube collides with any of the background objects, which is type is set to obstacle. If it does collide, then we work out the top of that object based on its position in the world and its height. And if our position on the y-axis is less than its height, we set the collision box's y position to that height. So what happens is the collision box dips down, hits the platform, collision box. Once that occurs, what happens is the Y position of the actor's collision box is then aligned so it's perfectly above that of the platform it's just collided with. As the, if I bring this back across here, as the past collision cube is a pointer, as you can see here, we can update its position inside the loop in the LevelManager and then return true to indicate we've hit a platform. Then what we do is we set the player's Y position to the Y position of the collision cube, and then we flip a boolean to say the player is no longer falling, and then we set another one to say the player is on the ground, and then we, in this function here, this is falling. So what we do here is, we could just do this actually, we subtract the entity state fallen, and then if the state flags equals 0, then we set them to the idle state for the entity, and also that the entity is on the ground. And then you'll also notice that the switch state animation function is in here as well, where we change the player back to the idle state. So if we didn't collide here, then we would just add the value of gravity to the so there's a value called jump speed, which is used to handle jumping and also falling. So first off, in the player's case here, before we do anything to the player's Y position, we first check whether they are actually on a floor or on a platform, sorry. And if they are, then we bail from it here. Otherwise, we have to adjust the jump speed value, then add that to the player's Y position, center the collision cube again, and then do another check to see whether we're on the floor. In fact, probably should put that back actually. They might not actually be falling at this. And obviously the same applies again here, the player state flags. And then you always set the player's Y position to the collision cube, so they are positioned on the platform. So if we've checked if they've collided with a platform and they have not, then we then have to change the collision box Y position by the adjustment value, just to remove the change that we did first off, and then return false. So this is kind of how we check whether we've collided with any of the platforms in the game. This applies to both the player and also the baddies as well. They use the same function with the adjustments here. So that's the collisions with platforms there. There's also another function for hit object here. So if the player wasn't actually falling, instead we were jumping, then you would be checking to see, once you moved up, if you actually hit an object at all. So what this does here is this hit object basically checks with everything. And then it's also used to see whether you've actually collided with the exit as well. So if you're jumping, you pass through here, and then it will be used to say whether you need to adjust the player's position. Initially I was using this with the platformer one as well, as there are a number of different times you're going to constantly kind of be checking for collisions. This one here is pretty much the hit object one is pretty much used when you're kind of moving around, and then the fall is kind of just used with the platform one really. So the jump code you can see in here, rather than returning a boolean, the hit object actually returns their ID, or rather the collision type. Sorry. So you see here, if it returns platform here, then we set fall into true, set jump into false, and then we make sure that we take off any of the jump speed we've added on previously. And then there's obviously a separate one here for coins only. This is where the collision types come in useful here, so we can literally restrict which objects we need to call the collision function with. So that's the way that the collision with platforms actually works. So the creating 3D levels from 2D maps, I think I've kind of already explained that really, so I don't really need to say any more about that. Like I said, you can find these online if you type into any search engine and then go on to images. You'll find some of the level maps in here. I think there was a specific site which was useful for this. I can't remember what it was now. Like that's like how I sort of found them. Like so it's a case of work out the size. If you're working with a different game, you need to work out what size blocks are actually make up the level, and then convert the map to like a pixel map like this. And then through trial and error, you'll have to work out what blocks make sense in 3D and which ones don't. And then you'll need to sort of test the level as well, as sometimes this won't be apparent to you until you actually play around with it. So jumping and falling, I've already covered the falling here, so let's cover the jumping code. This is probably the best jumping that I've actually got working before. So let's talk about some of that here. So in here we have some parameters that the player must stay within. So you see here we have the gravity of the player, the acceleration when jumping, and then one thing to note as well is the player's maximum speed. So in the scrolling code here, where is it here? So this is how the scrolling is handled. We center the camera over the player here. So you'll see here there's a boolean here for is it the start? And the reason why you pass is it the start is you want to restrict the left-hand side margin of the scroll window here. So like I said, at the start of the game the player's there, so if we were to center it over the player we would only see a small part of the level. So what you do is if it is the start, then you basically clip the window to 0 on the scroll so that you get to see the full distance at the start. So all this code here does is it tries to center the X and Y position. So you see here the we make sure that the first off we work out the left hand side of the window, make sure it can't be smaller than 0, and then we work out the right side of the window to make sure it doesn't go outside of the level, which is what it's doing here. We subtract the width of the window from the level's width in pixels if the right hand side is greater than that, and if it is we clamp it to that so it can't go any further. We then set the left hand side from this value here. And then what we do is if it's not the start, then we'll need to scroll some things. So what we work out is how far the scroll window has actually moved. This is where we use the old camera position here. This is the camera's, or rather this is the scroll window's old X coordinate. So you'll see here we convert it from a float into an integer. We then work out the new scroll position, and then we work out the difference here. So you see that the we could actually scroll. Well, I had the game at the first from the start. It was able to scroll left, but I sort of stopped that because otherwise entities respawn again, as in coins, and enemies which were killed will obviously come back to life again. So you need to be careful how far you, or what speed you kind of move at, because if it is larger than the size in tiles, then you'll end up creating gaps between one column of tiles and the next. So the player's speed should always be below 1. So one way you could get around that would be, I suppose, to pass in the difference speed. I guess I didn't do that here, but that's how you would kind of get past that here. So what this bit here is doing is it's working out the position in tiles on the Z-axis to where it starts drawing. So you see here what this is doing here is it's getting the left-hand side position, converting it to an integer, and if it hasn't moved a full tile in distance, then it returns. It only sort of works on like a full size of a tile. And then if this value is greater than 0, then we basically divide this by the depth of a tile. And then what we're doing here is we're making sure that the scroll window hasn't gone past the width of the level. So this is if you're scrolling left here, and then this is for if you are scrolling right. Again, each time they divide the X position of the scroll window by tiles to work out the data offset into the level data. So this would be the starting tile X position. So if these were kind of labelled here, this would be tile 0, 1, 2, 3, 4. That'd be tile 15 there. So to get to the next column, we need to add 15 to get there. Like so, this is just a constant add 15 or multiply by 15 to get the offset of this column from the data array. So once we get that, we then use the tile data pointer here to point to the start of a column, and then we just iterate over there and then add the objects like we did when we initialized the level, or add an enemy. And that's how the scrolling goes there. To have like a variable speed scroll, you would have to kind of add the movement speed to some of this here. again, the this here needs to be converted to tiles, and then you would kind of have to add that additional speed to the starting position somehow. So where was I here? Oh, yeah, I was talking about the 2D levels here. So I think I've explained all of that. So I'll get back to the jumping code for the player a moment. So when we press, in fact, what I'll do is I'll talk about what's actually happening between the player and the game itself. So in the game itself, it handles the input in there's an update controls function in the game core itself, where it's basically checking the joystick, see what ranges have been pressed and whether to create like a move order. So we have like one variable here which using different bit flags here. So these are the actions here using bit flags. So you'll see this is 1, 2, 4, 8, 16, 32, 64, 128 and 256 here. So these are the available actions here. As you can obviously move the sticks and press various buttons, we kind of stack them all together and then pass them to the player update code here. So the state flags handle not only what animation should play, but also what sort of things the player is actually doing. So this function here is bitset, checks the passed in player actions variable for the jump action. And then we also record a variable to say that the jump button is held. And then you'll see here we play a sound effect if it's the start of a jump. And obviously the player needs to be not jumping at all and not falling for this to occur. And then if the jump button is held down, and if the player is on the ground, if the player is not falling, and we're not currently jumping, then we call the jump start function. This then changes those flags. So at the start here we are jumping, we shouldn't be on the ground now, and we're not falling. We then set the jump speed variable, which is a float here. So this is kind of used as an acceleration on the y-axis, really. So if you put in a positive number here, the player will move up, and if you put in a negative number here, the player will go down. Or rather, once this value is added to the player's Y position, that will occur. So you see here we we set up a few things here. So we have like a jump limit. So what we kind of allow is for the player to have a variable jump height. If I come back to here and explain things a bit better here first. So when we check for jumps, we record how long the fire button or the jump button is held down for. And if the button is held down on each update while the there's like a jump height variable which can vary, and this is the maximum jump height. The jump can go up. So a quick button press will have like a smaller jump than one if you hold the button down longer, basically. And obviously we have various flags where we record these events. So the jump speed counter gets assigned the starting jump speed. Lots of this was trial and error to sort of come up with. Again, all these things you can kind of have a play around with. The key thing to note is you shouldn't have a jump speed that will make you jump larger than the height of a tile. So a tile height is 4 here. So this starts everything up. We set the player state flags to jump in. We then set the animation of the player to jump in. The jump counter is set to 0 and the held count is set to 0. So whenever you're jumping, the jump update function is called here, and then you'll see we record if that button, the jump button, is held down, and if jump start is set to true. So you'll see we have this here, and then if the jump limit is smaller than player jump count max, which is also in here, there we go, then we'll update the jump limit value. So what happens here is each time the jump update function is called, the jump counter is incremented. And if the jump counter reaches the jump limit or greater, then jumping is turned off, falling is set to true, we're no longer on the ground, and jump start is set to false. So if we come down back to the update bit here, so you'll see here, if the jumping is set to true, the jump update function is called, which does what I just explained. The player's Y position is added to the jump speed value. We then check for various collisions to see whether we've hit something above us. If we have, then we turn off jumping. So you see we are checking for obstacles and platforms as well. And then we also play the animation there. And then if we are not jumping, then we check to see whether we've actually collided with an enemy here. If we have, then the player state is set to dying. Of course, we could also be falling, in which case the fall function is called, which I pretty much went over earlier, so I won't go over too much detail here. First off, we check without updating the fall, if they're on a platform or not. If they're not, then you'll see here the jump speed. Then if it's greater than minus gravity, the fall speed is subtracted from the jump speed up to the maximum value of minus gravity. And then we can, while we're falling, if we hit a baddie, then we kill the baddie by calling the kill baddie. And the baddie collision function returns the ID of the Goomba you collided with, or -1 if there is no collision with anything. And you'll see if you hit a baddie, then jump start is called again, so you kind of bounce off of them slightly. And then there's also like the animation play function here. And then if your Y position goes below 0, then it means you've gone along the level and you've fallen down a hole like this. So on the level, the 0 is always at the bottom here. So you can think of tiles as basically going up from 0. So that's basically that there for the player. So if you are not jumping or falling, then there's always a check to see whether you've hit a baddie or not. And then there is variable friction to the player's speed. So you'll see we have jump speed and player speed. So the player speed is the normal sort of movement speed on the X and Z axis. You see we always, depending on if you're on the ground, that depends what sort of animation is going to be playing. You see we have the thing from the previous video where the walking animation code is used again. And then this function, the move entity function, which is a utility function for moving actors depending on their Y rotation or yaw. So if I quickly go over that. All what happens there is you pass in the position of the entity, and then based on its Y angle here. So you pass in the speed they're moving and possibly the strafe value. So the strafe, which is not used in this game, but obviously it could be, that's like a moving to your left or your right, regardless of your orientation. That just uses the sine function here and the player's angle. So you do this in two passes. You do the X axis first and then the Z axis next. It's important to split these two movements to enable you to have like sliding collision, as you can literally treat each movement on those axes as separate to one another and then update whichever collisions occur on that one axis, which is what happens here, where we check whether the players hit a wall or not. So if the player moves and they hit a wall, then we can just move with the reverse speed to undo that. And then each time we do this, we have to update the collision cube for the player. And then once we move them here, we're just making sure that they are still within the world, which is what the minimum x-axis and maximum x-axis does here. If I open this up again here, and start it and move towards this position here, you'll see I've stopped it so you can't fall off either side. So those are the x-axis there. However, you can fall off this way, just like that. So that's what they're doing. And then if you're not jumping and you're not falling, you've moved on the X or Z axis. We now need to see whether you could be on a platform or not still. And then also in here, where is it? Now, so we check to see whether you're on like a platform or not. If you're not, then obviously we set the fallen code again. So you kind of need to check whether you're on a platform after every time you kind of move, or even if you don't move, although I suspect here this block here basically only triggers if you have actually moved. Let's not change any of that. Actually, I don't want to break anything. So the second to last is the enemy movement here. So the enemy movements for the Goombas, pretty much, they use the entity move function, and they use the get angle 2D function here. So you pass in an X and a Y position. This is used for 2D really, but you can use it for 3D. So I'll jump into the baddie manager stuff here. So unlike the player, each of the baddies have their properties put into a structure to hold them. Lots of the stuff is same for the player. We have the falling on the ground. They have two different collision cubes. And then they have a load of stuff for the animations as well. And then you'll see we have a flag here for the maximum amount of baddies that can exist. So you will need to restrict that by level design. So potentially, if these pipes were not here and you were moving forward, all of these could potentially exist at the same time. So that's fine here, there's only 6. But if you didn't have this gap here, then they could follow you throughout the whole level until eventually you would crash the game because there would be too many of them active at any one time. So through your designing of the levels, you will have to work out how many you should have as a maximum number. Again, you kind of don't want to have too many of these because obviously they have a lot of properties to be checked for each time as they can fall. And then you also need to check whether they are on platforms themselves. So they have a lot of overhead associated with them potentially. Another thing with the baddies as well is they have initialize function here, which basically turns them all off at the start here. So at the start of a game or a level, you call this. It then clears them all out here by setting their states to 0, which basically is the same as a not alive. And then just like with the level objects, when the add baddie function is called from the level manager, there is a get free baddie function here, which has to go over the list and then check to see whether there is a free one to add. If there isn't, then obviously that's an error which you need to catch so you can update the amount of baddies that can be alive at any one time. And then just like with the other level objects, you need to use the ceiling value to position them correctly on the y-axis. And then you just initialize the scale of them, their collision cubes. I'm kind of going to brush over this pretty quickly here. The key parts which differ from the player are the movement bit here. So what happens is the baddie manager themselves where is it? I think when update is called on them, the game itself passes them the player's position. I'm not going to go over the game code in here as there's nothing really that new in here. This will be easy for you to figure out. So we have a movement position vector free in the play function here. in the game code, and once the player is moved, it assigns his position to the movement position vector 3, and then it also flips the z-axis as well. In fact, this is afterwards, sorry, this is afterwards. This is for the camera follow code here, where the z-axis is set to what it should be. So after the player update here, if the player is not dying, then their position is passed to the LevelManager update function. And then in the update function, so this block of code here, which is commented out, previously I was, in the last video, I did an animation for the Goomba dying, but then I kind of decided that there was no point using that. It was better to have the squashed Goomba models instead, replace the mesh of the animated Goombas. So that's why this is commented out here. So this loop here basically loops over all of the baddies to see basically if any of them are alive and active. If they are, then it calls the move function. So also notice in here there is a private variable, basically a vector3, which copies the player's position vector3, which is passed in, so that I don't have to pass a pointer to each of the movement function updates. So then what happens is we work out the player's position here. From the, basically we copy it in here. And then we use the getAngle function to work out which direction the player is facing, or rather the angle from the player's position to the Goomba's position. So the Goomba's position is put into this one here. The player's position is put into this one here. You pass the target at the end as a vector3, and then you pass, in this case it's the X and the Z positions of the player to work out the angle from that. We then add 270 to that angle via the wrapAngle function. And the reason for that is the angle returned is off by 90 degrees. So we're basically converting that angle from the maths to the world angle. And then after we've added 90 degrees, because that's what the return value is off by, we then add a further 180 degrees to that value to give us the opposite value to that. So that basically means we are facing in the opposite direction to what the player is moving, so we end up moving towards them. So this is what creates the tracking for the Goomba there. So this just sets what angle we should be moving towards. And then all what happens is if the Goomba is on the ground, then we move them. If they're not, then obviously they'll be falling. And then we just do the same sort of stuff as we did before. We check whether they're on a platform. If they are, then we set on ground to true and fall into false. If they're not on a platform, then we obviously set them to falling. And obviously we have to keep updating the collision cube for them as well. And then there's also another one here to check whether we hit a wall or not, which is what the hit object function does here. It basically allows them to have the sliding collision as well on the X and Z axis independently. So I think that's kind of covered everything I want to cover here. So one other issue I'll talk about here, which I've briefly mentioned, was the lighting issues. Unfortunately, I do not have the pre-code before I had the lighting on. So I've got a number of different versions of the same game here. Usually every time I kind of add something which I consider to be a game-breaking event or action, I'll make a backup of the game. So initially, this version here, I was running everything just in the title screen code, which is normally what I do. The problem is there was various glitches after I added lighting. So in the scene 3D here, using some of the example code that comes with LibDragon, I decided to add in a light to the scene to make things look a bit better, because it was very bright beforehand. So what this did was it basically was cutting off the bottom of the pipes here, which is why I flipped the pipes from being on. So initially the pipes had their origin at the bottom left there, and then every time there was a pipe tile, I would create another pipe part, which would be positioned on top of itself, just like this. So a free height pipe would be positioned like this. And then I would put the pipe top on top there. But what was happening, unlike here where you cannot see the splits, for some reason the lighting function was creating invisible slices wherever they connected. This does not appear in the Ares emulator, would not show up in here. It only shows up on the real N64, which was very irritating, as fixing the issue, I had to keep transferring the code back to the real machine each time, as the emulator couldn't fucking see it. Sorry, pardon my language. The emulator couldn't see it, which was very irritating. So in the end, what I had to do to fix it was make the pipes with an origin at the top there, so they could be scaled on the y-axis to the correct height on the levels here. So you'll see in here where there's like tile segments, this is what I was doing initially. So I would have two pipe bottoms here and a pipe top there. But because the lighten function was splitting these for some reason, one of the things I tried doing first off was making them a bit larger by sort of extending them, but this still created the lighten glitch. So in the end, what I had to do was to just have one and then do it like this, where you have one pixel represent the whole pipe strip. Hence the different colours here represent what the height should actually be for the pipes. And that's how I fixed that. If you should come across that in your own code. I did try and play around with fog, but if you turn fog on, which I'll do now to show you, this happens. Everything becomes invisible. So it's kind of there, you can kind of make out. So I could not get fog working, so in the end I decided to just turn it off. Just make sure this works one last time. There we go. Right, so thank you for watching. This has been a very long video. Hopefully you will be able to get a lot out of this. Yeah, I've not covered everything, as lots of things I feel kind of were covered in previous tutorials, so there was no need for them here. If you have any questions about anything to do with the code, then drop me your question in the comments, and then when I sort of look next, I will give you an answer. So thanks for watching, and I will catch you in the next video, which won't be for the N64, as this is the last video for the N64, unless I discover some new things I think will be useful to you. So that's it for this video. Thanks for watching.